Hello, everyone. So let's talk about another Leetcode problem today. This is problem 703, kth largest element in a stream. So we have to design a class to find the kth largest element in a stream. Stream means that the amount of data is actually changing dynamically. So you keep on adding data, but even after keeping on adding data, you have to return the kth largest element of the whole stream, right? So it's not a fixed size input. You will keep on adding and still you consistently have to give the kth largest value in the whole input that has come so far. So note that it is the kth largest element in the sorted order, not the kth distinct element. That means if the stream has something like this, 1, 1, 2, 3, 4, if someone says the fourth element, it means 0, 1, 2, 3, 4. This is the fourth element, not the fourth distinct element. Okay, so there might be duplicates of elements. Okay, so the two methods we have to define: kth largest. You'll be given the value of k and the initial an initial array, and then which initializes the object with integer k and a stream of integer nums. And then we have this add, where we can keep on adding elements every time, but this one returns an integer. That means after we add something, your kth element may change, so you just return it. For here is the example. We first initialize the array with 3 elements. We initialize the kth largest object with this 4 element, and then given is like find the third element. Okay, so this is the initialization part. Okay, so here in the input in the first example, we see that this is the array that with which we initialize the object kth largest. And let's keep it sorted to make it more understandable. 2, 4, 5, 8. Okay, and we are also told that we have to always find the third largest. Okay, so after we add, say, 3, now you see the third largest is going to be 8, 5, and 4. So 8 is the largest, 5 is second largest, and 4 is the third largest. Then now we add 5. So it becomes 8, 5, 5, right? Okay, then we add 10. So the largest is now 10, the second largest is 8, third largest is 5. It returns 5. Okay. Next we add 9. So we add 9, the largest now is 10, the second largest is 9, the third largest is 8. So you have to return 8. And finally you add 4. So again, the first largest is 10, second largest is 9, third largest is 8. So you return 8. Okay. Okay, so how do we solve this? We can actually, you see, we actually are getting a stream of numbers. That means we'll be having more and more numbers. Now the intuition is like, the very naive thoughts might be like, can we add, like keep a list, a long list, right? And I just keep a list and just add to the list and sort it every time. Actually, that's not a very good solution, because you see there might be like millions of numbers coming, and I think just holding on to the values, they'll be like very smaller values, just holding on to them and then sorting them and also storing them with millions of values, it's going to be so like inefficient. Instead, why don't we just keep, like, is there a way just to keep, say, like 3 elements all the time? And if the new element is even larger, we just add them in that 3 element list and remove the smaller element, right? Can we do that? Just for here, for the example, say initially, if our thing had something like this, say, we always just kept, if we keep a list of 3 elements after adding 3, if we just needed this list, right? We didn't need to keep everything. And after adding 5, we could just discard 4 and add 5, right? If we could do something after adding 10, we could discard another 5 and add 10, right? So that is enough actually. So I don't need to store all the values and other things as the new numbers are coming. I just update this list and kick in the smaller value. Say I kick in the 5th value and add 9 here, right? Can I do that? 1098. So what is a good data structure to do that, and an efficient data structure? So you see that we have a fixed size data structure, and every time a new element comes, if that is a large element, we just kick out the smallest element. So can we think about a priority queue or heap, right? So if we say like this heap has a size of 3 for this problem, and it can be every time we want to remove the smallest element in it. So can I say, is it a min heap? By min heap, we say that this root element, like everything here, say if this is A and everything here is B, everything in B is like A is smaller than its children. That means everything here is larger. So if I have a min heap, so the min heap actually carries the large elements, right? So every time I have all the large elements in my heap, and the smallest of them is at the top. So if a new element comes, it just kicks out the smallest element and adds the larger element, and then recalculates the new smallest element. Okay, so let's try to code this. Okay, so we coded it. Initially, we had a priority queue, that is the object to initialize the initial array, and k is the value, like what is the, this is the value for the kth largest element. What is the value of, it contains the value of the k. And then we have this kth largest function. We initialize the priority queue and the value of k. We read from the initial array and keep on adding to the priority queue. But once the size of the priority queue grows beyond k, we just shred the top value. That means that will ensure that we just have the largest k elements in the priority queue. Okay, so the add function adds value to the priority queue, and we add the value, and as soon as the size of the priority queue is greater than k, we just shed the smallest element out of the priority queue. That means that the kth largest element will now be at the top of the priority queue, and then I just do a pick and return it. Okay, so let's run it. Accepted the test cases, and let's submit it. Okay, now the question is like, what is the time complexity of this algorithm? So what are the things that we're doing here? You see, we are running a for loop. This is the input. So if the input size is say like n, if the input size is n, then we are doing like adding to the queue n times. But the size of the queue always remains k. So add operation will take log k. So n times log k. That is n log k for this part. Okay, so it's n log k. Let's check the other parts of the code. And here, after every add operation, if I am doing these add operations, say m times, every time I am adding to a priority queue of size k, that means m operations will take, m add operations will take m log k. Okay, so this is ultimately n plus m log k, where n is the size of the initial array and m is the number of add operations. Okay, so there goes the time complexity. The space complexity is, you see we have a priority queue, and this is the extra space that we're using. And the maximum size of this priority queue is going to be k. So space complexity is going to be, so this is the time complexity, and the space complexity is going to be order of k. Okay, so thanks everyone for watching. I hope this one helped you understand like in what kind sort of problems we can think of using priority queue. Usually the key, keep attention if the problem says like kth largest, kth smallest. In all those problems, priority queue is a candidate data structure.